This video will cover Chapter 2 of the OCR A chemistry specification. It will hit all of these points outlined on the right side of the screen. Now, along the video, I will be referring back to some of these points. You can find this information on these pages of the Kerboodle textbook. So, let's get started. Now, subatomic particles. There are three main subatomic particles that you must be aware of for OCR chemistry. First one being protons, which are positively charged subatomic particles. The next one being neutrons, which are uncharged subatomic particles. And the last one being electrons, which are negatively charged subatomic particles. Now, there are properties of these subatomic particles that we must be aware of. The number one being mass. Masses of these subatomic particles are too small to be measured empirically with units such as grams, milligrams, and so on and so forth. So we use relative masses. Protons and neutrons have the same relative mass, which is 1. Electrons, on the other hand, have a negligible mass, the exact mass being 1/1836. Now, I don't believe you need to know this number directly, but just in case, it's very good to know it. The main statement, however, is negligible mass. Extreme accurate measurements do show that the proton weighs more than the neutron, but for OCR, all you need to know is that they weigh the same. Now, charges. As we run through them before, the proton has a positive charge, electron has a negative charge, and neutron has no charge. Now, the charge of the proton and the electron are the exact same, but they're just opposite. For instance, if you were to put a label on it, the electron would have 1.789 plus, but then minus. Then the proton would have the exact same value, but just negative. So this is a quick overview or summary of all of those properties that we just ran through. The proton, the abbreviation being P+, relative charge 1+, relative mass 1, neutron, abbreviation N, relative charge 0, relative mass 1, electron E-, charge 1-, and relative mass is 1/1836, or negligible. Now, just to be really careful, the relative charge shows the symbol after the number. That is something that you must be aware of. Now, mass number and atomic number. In the periodic table, you'll see the elements presented as such, with the chemical symbol being here and two numbers top and bottom. The bigger number is always the atomic mass. Now, the reason why I say bigger number is because it does not have to be in this order, where the bigger number is lower than the smaller number. Sometimes they may give it to you where the bigger number is on top and the smaller number is on the bottom. Either way, you need to know that the bigger number is the atomic mass. Now, the atomic mass is the number of protons plus neutrons. The smaller number, on the other hand, is the atomic number. This is just the number of protons. Now remember, because the electron has negligible mass, it is not present in either of these numbers. So, moving on. There are a few definitions that you must be aware of in this chapter, one of them being isotopes. Now, isotopes are, I'll write it down first. Now, the definition is isotopes are atoms of the same element but with a different number of neutrons and therefore different masses. Now, examples are oxygen 16 compared to oxygen 17. Now, as you can see, they have a different number of neutrons. The reason why you can see this is because the bottom number, which is the smaller number, is the number of protons. These stay the same between both isotopes, but the masses differ, right? Which is in the definition. And if we were to do 16 minus 8, that would give us 8. 17 minus 8, that would give us 9. So that means this isotope has one more neutron. But of course, the number of protons, which is this number, stays the exact same. Now, there are two bullet points that you must remember for isotopes. The first one being they have all isotopes, have the same electronic configuration. Hence, the same chemical properties. Now, there's a very specific phrase that you must remember in this bullet point, which is this: the same electronic configuration. You cannot say they have the same number of electrons. You must say electronic configuration. Now, this becomes more relevant later on in the specification, but for now, you just must remember same electronic configuration. Now, the reason why this is important is because it shows that it has the same chemical properties, meaning that this oxygen and this oxygen will react the exact same in a reaction because they have the same electronic configuration. The only thing that determines how a reaction takes place is how the electrons react with one another and how they interact. If they have the same electronic configuration, they will interact the exact same. But they do have different masses. So what does that mean? Well, that's covered in the next bullet point, which is different physical properties. Now, what does this mean? Well, this means that, of course, the electronic configuration is the same. So chemical properties, exact same. But physically speaking, this oxygen and this oxygen are not the exact same. So this is what differentiates something like heavy water, right? Heavy water is a water with more neutrons and therefore a greater mass than regular water. That means that it is denser, right? So that's a different physical property. Now, that physical property, again, has absolutely nothing to do with the chemical properties. But because the mass is different, the physical properties will also be different. Now, there are two more definitions that you must remember. The first one being relative isotopic mass. And I'll write that down first. Now, the definition of relative isotopic mass is the mass of an isotope relative to a 12th the mass of carbon-12. Now, you don't exactly have to understand what that means, but just the definition itself. A lot of the time it's in exams, they will purely ask you, state the definition of relative isotopic mass, and you put this down, and it's an easy 1, if not 2 marker, right? Now, there is another one, which is the relative atomic mass. Now, although there's a slight difference, they are pretty much the exact same. I'll write the definition down first, and then I'll highlight the difference. Now, as is very obvious, the main difference is this statement right here. It is the weighted mean mass of an atom of an element, right? Now, as I said before, you don't entirely have to understand the definitions really, but just so we have a better understanding later on of something that I'm going to bring up, I do want to describe it. So, relative isotopic mass. So, as we spoke about the isotopes before, the isotope is the atoms, sorry, let me just change that, atoms of the same element with different number of neutrons and different masses, right? So, this is talking about the relative masses of each one of these, each individual isotopes. That's why it says the mass of an isotope. But when we're talking about relative atomic mass, it tries to figure out the overall, or as it says in the definition, the mean average mass of all of the isotopes. So for instance, if I had a cloud of oxygen, I'd have oxygen 16, oxygen 17, oxygen 18, and yeah, so on and so forth, right? So this means that as a scientist, I want to take out the relative atomic mass, which is just, okay, fair enough, I have all of these isotopes, but if I wanted to put it down in a periodic table, what is the mass that I should put down? Well, that's what relative atomic mass is trying to dictate. And we have to work out how we figure out the relative atomic mass. Now, the relative atomic mass, this takes into consideration two things. First one being the percentage abundance of each isotope. And the second one being the relative isotopic mass of each isotope. So then, what is the equation for relative atomic mass? Well, the equation for relative atomic mass, I'll just write it in short, is the isotopic mass, or isotopic masses, times by their percentage abundancy, all over 100. Right, so using this as an example, we'll do this question. So, the relative atomic mass of a sample of osmium can be determined from its mass spectrum, shown below. So, mass spectrum we've already talked about. It shows the relative abundances of each isotope, of each isotope at their mass. Sorry. Calculate the relative atomic mass of osmium in the sample. Well, let's start this with using the equation. So the equation says isotopic masses times by their percentage abundances. Well, ideally this should be sum of. So, using that equation, we can do 12.13, which is the percentage abundancy at 188, times by 188, plus 16.75 times by 189, plus 27.23 times by 190, plus 43.89 times by 192. So using this, we can see that this, what I just did here, was the percentage abundancy at each relative atomic mass, multiply them together, and then have the sum of all of that. And then we just divide that all by 100, giving us an answer of 190.47 to 2 decimal places. Now that's very simple. Of course, they may not always give it to you in a graph like this, but they will give you the percentage abundances and the isotopic masses always. So whenever you see a calculation question on relative atomic mass, remember that this is the formula that you use and this is how you calculate it. Okay. Determining relative atomic mass spectrometry, right? So this is what the question just said. Now, how does a mass spectra work? A mass spectra works in 4 bullet points, right? So the sample is first placed in the mass spectrometer. Then the sample is vaporized and ionized to be ions, right? So you have the sample, you want to put it into a mass spectra. What you do is you put that sample in the mass spectrometer, and then you vaporize that sample, and then you ionize it, right? So now it's become an ion, so it's positively charged, right? And then these ions, which are those positively charged isotopes now, are accelerated where the heavier ions, based on their isotopic mass, are slower and therefore less deflected. And then lastly, these ions are detected by mass spectrum as a mass charge ratio. So what this machine is basically doing is, if you have a machine such as this, there, and then you have your detector over here. So you put the sample in here and it's ionized, right? So now this sample, so you put the sample in here, vaporized. Here, they're ionized. So some of these, or all of them actually, would be, for instance, magnesium plus, all right, magnesium plus 2, or whatever. But depending on their isotopic masses, when they exit through here, you can see there's a little curve here. The heavier ones will be slower, and therefore they will be less curved. So that means there. So the detector will pick up one there, and then there. The detector will pick up one there. Because this one is less deflected, we know that this one has a higher isotopic mass, or a higher mass charge. That's how it will come out. And this one, because it's more deflected, will be a lower isotopic mass, or a lower mass charge. Okay. Charges. Now, the periodic table gives us a lot of information. One of the key ones being the charges of the elements at each group. So this is group 1, group 2, group 3. Group 4, we were not allowed to, we're not able to tell the charge of those elements based on that group. So we skip that and group 5, group 6, group 7. So group 1 is +1, you can see that. Group 2 is +2, group 3 is +3, group 5 is then -3, and then -2, -1, right? So that's H plus for hydrogen as an ion. That's magnesium 2 plus, +2, 2 plus as an ion. That's boron 3 plus. That's oxygen 2 minus, so on and so forth. Now, there are some charges that you have to memorize for OCR because you're not able to tell them through the spec. You're not able to tell them through the periodic table, and you have to just memorize them, really. That's zinc 2 plus, Ag plus, and then all of these polyatomic ions. Ideally, over time, you will memorize them just because you'll be using them so much throughout the years. But it's good to just have them down somewhere. Right. Now, another key thing is how to write formulae of ionic compounds. For example, hydrogen sulfate, right? So we know hydrogen is plus, and sulfate is SO42 minus. So number one is to identify the ions involved. So it's hydrogen plus, sulfate, SO42 minus. Then we use the crossover method. So it's hydrogen with a plus charge, a 1 plus charge, SO42 minus as a 2 minus charge. So this charge crosses over down here, and this charge crosses over down here, giving us H2, because that 2 minus charge from SO42 minus dropped down, SO4, because that 1 plus came down and we don't have to write 1. Now, state symbols, very important. Metals plus metal oxides give you a solid. Anything to do with water will always be a liquid. So water, H2O, is the only liquid state symbol, unless stated otherwise, of course. Gases, which are group A, are always gas, and anything else is just aqueous. Now, how do we write an ionic equation? So, using this as an example, which is K plus NaCl plus KCl plus Na. As an example, we'll write out an ionic equation. So now pay attention to the state symbols. It's very important. So first is we balance where necessary. Now this equation doesn't need any balancing. If there was an equation that needed balancing, you just balance both sides. Then we split all the aqueous into their ions, right? So doing that, we know, let's write it out again. So this is potassium, which is a solid, so we won't need to split those up. NaCl, which is aqueous. KCl, which is aqueous. Plus Na, which is solid, we won't need to split that up. So let's split these two up, gives us Na plus Cl minus. Split these two up, it gives you K plus Cl minus. Now, second part is to cancel out any repeated ions. So let's just write out the ions. We don't need to write out the whole thing just yet. K plus Cl minus. Well, we can see on both sides of the equation that Cl minus repeats. So let's just cancel those out. And now we rewrite the whole equation. So that's K solid, remember to include that again, plus Na plus, which is aqueous, of course, goes to K plus, which is aqueous, plus Na solid. Now, if you just go about it with these steps, you'll be able to identify any ionic equation. And that's it for this chapter. I hope you learned something, and I hope it's been helpful. These do come up in every single paper, so make sure that you memorize all the definitions that you need to memorize and all the methods that you need to memorize from this chapter. Thank you.